Dear student, this is the last class of this series in which we were studying on the partial differential equation, on the chapter partial differential equation, and this is lecture number 50, and it is the final and last lecture of this for this chapter. And in this class, we will solve some partial differential equation. Just we solve here some partial differential equations, nothing else. Okay. So let us now go to solve some differential equations. Number one, since we have solved 6 problems before this class, that is in the last class, and so the problem, the serial number of this problem is 7. Here is the problem: a tube of internal radius R1 and external radius R2 is heated along its axis. The temperatures of the inner and outer surfaces at steady state are θ1 and θ2 respectively. Calculate the temperature distribution along the radial direction and also the thermal conductivity of the material of the tube. So from this problem, you have to remember two things. Number one is steady state. Here steady state is mentioned. So just remember this one, steady state. And then another one is the distribution along radial direction, and these two terms will be referred in this problem. So just remember steady state and radial direction. In the radial direction, distribution of heat temperature along the radial direction. So now, since the steady state has reached, so the heat conductivity equation reduces to the Laplace equation, because you know that in case of steady state solution, steady state condition, del theta by del t, that is the theta is the temperature function, or del u del t, that becomes 0, and in that case the right hand side of heat conduction equation just reduces to Laplace equation. Just go our previous class and then follow the just look at the heat conduction equation, and there if you write del u del t is equal to 0, then what happens, just check this, and you will better understand that will give you Laplace equation in two dimension. In this case it is 2 dimension, so the Laplace equation in 2 dimension in polar coordinate can be written as 2-dimensional polar coordinate can be written as 1 by r del u del r plus del 2u by del r square, that is equal to 0, where u is equal to temperature, because in the steady state has been arrived. So from here you can write d del r of du dr, that is equal to, this can be written as del r of del u dr del r, that is equal to minus 1 by r del u del r. This is equation number 1. Now let us consider that v is equal to del u del r. Just substitute the value of v taken in such a way that v is equal to del u del r. Then from this equation one can write, since del u del r is equal to v, so del v del r will give you the left hand side, that is equal to minus del u del r is v, so minus v by r, and from here del v by v, that is equal to minus del r by r. Now integrating both sides, we have from the left hand side log v, that is equal to minus log r plus log c1. C1 is a constant. So from here you can write, if you take this term in the left hand side, so log v plus log r, that give you log v into r, that is your log c1, and from here v into r is equal to c1, or v is equal to c1 by r. Since v is equal to del u del r, since you see from here that v is equal to c1 by r, okay, and you also know that v is equal to del u del r. So from this expression, from this relation, you can write del u del r is equal to c by r, and from here del u is equal to c1 del r by r. So again integrating both sides, we have these will give you u, integration of del u will give you u function of obviously r, that is equal to this c1 is here, then this will give you log r, and there will be another constant, that is c2. So finally we have u1 is equal to c1 plus c1 log r plus c2. This is the solution of the conduction heat conduction equation when state reached in two-dimensional polar coordinate. And now we have to calculate the value of C1 and C2, which are arbitrary constants. Now we have to employ the boundary conditions. So one of the boundary condition was that at R1 U is equal to theta 1. That is written here. That is clearly written as that theta 1 and theta 2 respectively when for the inner and outer temperature. And see here the internal radius is R1 and the outer radius is R2. So at R1 theta is theta 1 and at R2 theta is theta 2. So here is that, here is that, here is that. So here from here, so the boundary condition is that R is equal to R1 theta U is equal to theta 1 in this case. U is the temperature function, and at R is equal to R2 U is equal to theta 2. So from this relation you can readily write theta 1 is equal to C1 log R1 plus C2 and theta 2 is equal to C2 log R2 plus C2, just using these boundary conditions. Now subtracting the second one from the first one, we can write, so this will give you, this will theta 1 minus theta 2, that is here, and from here C2 will cancel each other, and these two term from these two term C1 log R1 minus C1 log R2, that will give you C1 log R1 by R2, that is equal to theta 1 minus theta 2. So from here C1 is equal to theta 1 minus theta 2 by log R1 minus R2, that is equal to theta 1 minus theta 2 by log R1 by R2. This is equation number 3. Also from this expression, from which expression, from any one this, let this from this expression, C2 is equal to theta 1 minus C1 C1 log R1. That will lead you, that will give you theta 1 minus theta 1 minus theta 2 into log R1 by log R1 by R2. Just substitute here the value of C1 from here to this relation, that is here. This is equation number 4. Then from equation number 2, that means from this equation the complete solution, that is UR, or you can write it as theta, that is C1 log R plus C2, that will give you UR, that is equal to theta, that is equal to, here is the value of C1 theta 1 minus theta 2 by log R1 by log R1 by R2 into log R plus the value of C2, that is theta 1 minus theta 1 minus theta 2 into log R1 by log R1 by R2. And from here just take 1 by log R1 by R2 as a common term, then this will give you theta 1 minus theta 2 log R plus theta 1 log R1 by R2, then minus theta 1 minus theta 2 log R1. So if you take this as constant, that will be theta log R1, theta, because this is the theta 1 term, so theta into log R1 by R2 will be here. Okay, no problem. So just first do this subtraction. So from here you have to, this term will give you theta 1 into log R1 by R2 into theta 1 minus theta 1 minus theta 2 by into log R1 by log R1 by R2, then log R1 by R2 can be taken as common term. So this will lead you this, this will give you this. Now after simplification, this here simplification is done here. This is written here as here, and this is written in two parts, that is theta 1 log R1 then minus theta 1 log R2, and that is just decomposed here. So after doing some simplification, you finally get theta function of R theta, that is equal to 1 by log R1 by R2, theta 1 minus theta 2 log R plus theta 2 log R1 minus theta 1 log R2. This is equation number 5. This gives the distribution of temperature along the radial direction of the tube. So in the radial direction of the tube. So now we are here to find out the value of d theta by dr. D theta by dr. So that will give you, this is the common term, that is 1 by log R1 by R2. Then only this term will be there. The term coming out from this term will be there. So that is here theta 1 minus theta 2, and differentiation of this is give you 1 by R. That is equal to theta 1 minus theta 2 by R into log R1 by R2. This is equation number 6. Now from the definition of conductivity, you know that d theta by dt is equal to minus Ka d theta by dr. This is the definition of conductivity, where K is the on thermal conductivity. A is the cross section, and if the temperature gradient of theta temperature is theta by dt, then that would be minus Ka theta by dr. That is the temperature gradient of theta with respect to r. So now from equation 6, here is equation 6, you will know that theta by dr is equal to this. Just substitute this value in this equation. So theta by dt is equal to minus Ka, then theta 1 minus theta 2 by r log r1 by r2. So that will lead you K is equal to minus, this minus is here, and the value of K is calculated from this expression. That will give you r log r1 by r2 by theta 1 minus theta 2. Then into this will be in the denominator, that is 1 by 2 pi rl. Cross section is cross section is 2 pi rl. 2 pi rl, and then this by dt, because L is the length, A is equal to pi rl. The actually cross section is equal to give you this is the cross sectional area of the tube. Cross sectional area of the tube, that is 2 pi rl. Okay, that is equal to the now here from this relation you can write K is equal to minus log r1 by r2 2 pi l theta 1 minus theta 2 theta by dt. These are cancel each other. So this is the expression for the thermal conductivity. So finally we get the relation for thermal conductivity. Now here is another problem. Find the solution of the following differential equation: del 2 psi by del x square plus del 2 psi by del y square is equal to 0 inside an annular region bounded by the circles x square plus y square is equal to r1 square and x square plus y square is equal to r2 square. That satisfied the condition psi is equal to psi 2 at r is equal to r2, and del psi by del r is equal to k by r1 at r is equal to r1. These are the boundary conditions, two boundary conditions. These are the. So here now rewriting the expression or the differential equation, partial differential equation that is given in this problem. Here is that del 2 psi by dx square, that is plus del 2 psi by del y square is equal to 0. Now I am writing this as equation 1, and this equation is the well-known Laplace equation. You know it in two-dimensional Cartesian coordinate. Now it is easy to solve it when once it transferred to polar form. So in case of polar form, polar coordinates, you know that the Laplacian operator has the form del 2 del r square plus 1 by r del r. So just rewrite this expression or convert this expression into two-dimensional polar coordinate. Then that will give you del 2 psi by del r square plus 1 by r del psi by del r, that is equal to 0. And from here you can write this term can be written as 1 by r del r del psi by del r, because if you compute this, that will give you this, because first you differentiate this term. So 1 by r into psi by dr, that will give you this, and then this is taken if you take it as constant. No, then if you differentiate this term r, then that will give you 1 by r del psi. So this term can be written as this, that is equal to 0. So from here del r of r del psi by del r is equal to 0. That is just write this first. So from here also you can write. So if you integrate this expression, you can obtain that r del psi by del r, that is equal to constant, and you say this constant is a. So from here you can also write del psi by del r, that is equal to a by r, and then also you can write del psi is equal to a by r del r. Okay, so now integrating this expression, you will get psi is here, that is equal to a by r. Here is a by r. So 1 by r will del r by del r, del r by r will give you log r. So a into log r plus another constant b. So the solution of psi becomes psi is equal to a log r plus b. This is the complete solution for psi in case of polar coordinate, two-dimensional polar coordinates. Now you also just follow equation number 2. What was there? There was del psi by del r is equal to a by r. Just adopt this one. Del psi by del r is equal to a by r from this expression, equation 2. Now use the boundary condition that del psi by r at r is equal to r1 is k by r1. That is, you have that boundary condition here, that del psi by del r at r is equal to k by r1. That is done here. That is done here. That is done here. Here is that. Here is a del psi by del r at r is equal to r1 is equal to k by r. It is given. So you also know that del psi by del r is equal to a by r. So if you use r is equal to r1, then del psi by del r also give you a by r1. So just compare these two, you will have a is equal to k. Then from equation number 3, you can write psi is equal to k log r plus b. This is equation number 4. Now the boundary condition that was given, that psi is equal to psi 2 at r is equal to r2. What that is here? That is given here. Psi is equal to psi 2 at r is equal to r2. Just use this boundary condition. Use this boundary condition in this expression. For this expression, then psi 2 that will give you equal to k into log r2 plus b. And from here b is equal to, b can be calculated, b is equal to psi 2, from here psi 2 minus k log r2. So finally the solution from this expression becomes psi r is equal to first k log r, then the value of b psi 2 minus k log r, k log r2. So this is the final solution, and that is also written here. And so the result solution is also here also you can write psi r is equal to, these two terms is taken in one term, that is psi 2 plus k ln r minus k ln r2 will give you k ln r by r2. So the complete solution is here, psi r is equal to psi 2 r plus k ln k log r by r2. This is the complete solution. Now another problem is here. Write down the three-dimensional equation of the heat flow through a medium of thermal conductivity K. Show that under steady condition, just stress this words. Steady condition. This reduces to Laplace equation that square u is equal to 0, where u r denotes the temperature. Using spherical polar coordinates, verify that the above has the solution, that is this has the solution of the form ur is equal to q by 4 pi k r plus b, where q is the rate of isothermal heat flow from a point source at r is equal to 0 and b is a constant. Another condition is here, that is, if the temperatures of the two concentric spheres of radii r1 r2 with the point source at the center be u1 and u2 respectively, show that u is equal to 4 pi k u1 minus u2 by r1 minus r2 into r1 r2. There are two conditions you have to put two identities, that is, one is this and another is this. Two problems. So now here the three-dimensional, you know that the three-dimensional heat flow equation for a medium is given by del u del t, that is equal to h square grad square u. Grad is nothing but this is Laplacian operator. So here you should remember that h is equal to k by rho s, where k is the conductivity of this medium, rho is the diffusivity, and it is called k by rho s, that is equal to h is called the diffusivity of the medium, and rho is the density, and s is the specific, and k is the conductivity, coefficient of conductivity. So now under the steady state condition, you know that there will be no heat flow. That is that there will be the gradient of heat flow with respect to t. That means del u del t will be 0. So from this relation you can write h square grad square u is equal to 0 or grad square is equal to 0. That means del u by del x square plus del u by del y square plus del u by del z square is equal to 0, which is the celebrated Laplace equation. So the first problem is here. So in case of steady flow, the heat equation becomes to Laplace equation. So first part is proved here. Now it is better to solve this type of problem in spherical polar coordinates. So if you write this expression in spherical polar coordinates, you have to first recall the Laplacian operator in spherical polar coordinates. The Laplacian operator in case of spherical polar coordinates can be written as r square del 2 del r square plus 2 r del r plus 1 by sin theta del theta plus 1 by sin square theta del 2 del phi square, that is equal to 0. So if you use this Laplacian operator for spherical polar coordinates on the temperature function u, you will get this expression. Since in the present case heat flows out radially, this was given in the problem, then that the heat flows in radial direction. That is, in that case, there will be no theta and phi component. Only radial component will be there. So, we are very lucky in this problem that these two terms can be cancelled in this case. Not can be, should be cancelled in this case. So, the problem now becomes r square del 2u del r square plus 2r del u del r is equal to 0. Remember why these two terms cancelled here, because the heat flow is found in only in the radial direction. So radial component, that means in the earth component will be there, but there will be no theta and phi component. So then this equation reduces to this, and this can be written as del r square del u del r, that is equal to 0. So from here, if you integrate this expression, you will get r square del u del r, that is equal to constant, say it is a. So del u del r is equal to form this relation a by r square, or del u is equal to a into del r by r square. This is equation number 4. Now once again integrate this expression, you will get del u, this will give you u, and that is equal to a by r with a minus sign. That is minus a by r plus b, another constant. So from the definition of q, you know that q is equal to minus k into d into du dr. In this case, since I have taken a as a constant, so actually we know that q is equal to minus ka du dr. Okay, so there will be a mismatch of this a and this a, so I write this as d. This is nothing, d is nothing but the area. So the definition, from the definition of q, you can write q is equal to minus k into d into du dr. Obviously where d is equal to 4 pi r square. So that is written here, minus k into 4 pi r square, and then del u del r. So q is equal to minus 4, this minus is there, k into 4 pi r square, and then from this expression, or here also it is written here also del u del r is equal to a by r square. So just use this value here, del u del r. So a by r square is here. So simplify this, r square will be cancelled out, so that will give you minus 4 pi k into a. A means this a is constant, and from here a is equal to, from this expression a can be calculated. Also from here you can write q is equal to minus 4 pi k. This is equation number 6, right? It is equation number 6, and from this equation you can write a is equal to minus q by 4 pi k. So this is the value of a, and this is the value of q. And now from equation 5, that is, this is the equation number 5, you have u is equal to minus a by r. So a is this, so this minus will give you a plus sign, so plus q by 4 pi k, and this r is here, and plus b is there. So from equation 5, that is following this equation, you have the solution of u as q by 4 pi k r plus b. So now the boundary condition that was given are, using the boundary condition, that is at r is equal to r1, u is equal to u1, and at r is equal to r2, u is equal to u2. Then from equation 5, that is from this equation, you can write u1 is equal to minus a by r1 plus b. And for the second case, that is r is equal to r2, that will give you u2 is equal to minus a by r2 plus b. That is written here. Now just subtract the second one from the first one. That will give you u1 minus u2, that is equal to a into 1 by r2 minus 1 by r1. This will cancel, b will cancel. And from here, a into r1 minus r2 by rr1 is equal to a, that is equal to u1 minus u2. So you can write from here a into r1 minus r2 is equal to u1 minus u2 into r1 r2, and from there a is finally calculated as u1 minus u2 into r1 r2 by r1 minus r2. So here a is computed. Now from equation 6, what was there? Equation number 6 was q is equal to minus 4 pi k. Just adopt this expression here. Q is equal to minus 4 pi ka. That will be equal to minus 4 pi k is here, and just substitute the value of a from this. That is here u1 minus u2 by r1 minus r2 into r1 r2. Okay, and this can further be written as q is equal to 4 pi k u1 minus u2. Since negative sign is there, so this can be written as R2 minus R1. So that is there R2 minus R1, and then here R1 minus R2. Okay, this is the required equation for Q. That was one that was that has to prove in this solution, in this problem. So now another problem: the displacement y of a viscously damped string is given by del 2u del 2y by del t square is equal to c square del 2y del x square minus 2k del y del t. Find the general solution of the above equation by the method of separation of variables. So you have to solve this problem, solve this equation. Here is the equation. I have written it once again. This equation is here, and this is equation number 1. Now to solve this equation, you just write y xt is equal to xx and tt, and then substitute all the values of the partial derivatives. These, and these, that is del 2y del t square del 2y del x square del y del t in this expression, and that will give you x d2 t by dt square, that is equal to c square t t d2 x dx square minus 2k x dt by dt. So dividing both sides by xt, that will give you 1 by t d2t by dt square minus, that is equal to c square by x d2x by dx square minus 2k by t dt by dt. And from here you can write this, just take this term in the left hand side, that is equal to 0. And from this expression you can see that the left hand side is the function of only t, that is it is independent of x, and the right hand side is the function of x only, that is it is independent of t. So both of them are constants, and say this constant is equal to minus omega square. So this expression, so therefore this expression now decomposed into two ordinary differential equation. One is 1 by t d2t by dt square plus 2 by t dt by t, that is equal to minus omega square, and that can be written as d2t by dt square plus 2k dt by dt plus omega square t is equal to 0. And to solve this for this equation, you can take as t is equal to e minus mt as the trial solution. Then dt by dt is equal to this, and d2t by dt square is equal to plus m square equal. This is plus m square equal to minus mt. Now substitute this value, then this will give you m square minus 2km plus omega square is equal to 0. Now you are looking for the values of m. So from this equation you can use the well-known Sridharacharya's formula, that is m is equal to minus k minus b plus minus root over v square minus 4ac by 2a. So that will give you here minus b is means 2k plus root over b 4b square means 2k whole square, that is 4k square minus 4ac, 4 a is 1 and c is omega square by 2 into 1, that will give you k plus minus root over k square minus omega square. So the solution is now tt is equal to a1 e to the power k plus root over k square minus omega square t plus a2 minus k minus root over k square minus omega square t. This is the solution for t. Now another ordinary differential equation that will give you this expression is c square by x d2x by dx square, that is equal to minus omega square. So that is written here, and that from here you can write this, and you know that this has this, and if you use the similar process that we employed in this case, then you will have two values of m, two values of m, and that are plus I omega by c, and another is minus I omega by c. So that will lead to a solution for x as b e to the plus minus I omega by c into x. So that can be written as also b1 cos omega x by c plus b2 sin omega x by c. This is equation number 5, and this is the solution for x. Now if you wish to find out the complete solution, then that will give you b1, this term is written first, and then the solution for t is written after that. So that is the complete solution. So here, there, and three cases here to be considered that are here listed. So just go it, just view it, look at it. Nothing is to do here. Now the next problem is a function phi xt. The function is given as phi xt satisfies the wave equation where x is the Cartesian coordinate of the field point and t is the time. Write down the differential equation of the differential equation. This is the first thing you have to do, and then obtain the possible solutions of this equation by the method of separation of variables. Consider only those solutions which vary simply harmonically with time. So the given equation, given function is phi xt, and if it satisfies the wave equation, then you can write del 2 phi by del t square is equal to c square del 2 phi by del x square. And to solve this, you can write phi xt as this. And now substitute the value of these partial derivatives in this expression. You will get x d to t by dt square is equal to t into c square dt x by dx square. And dividing both sides by xt, that will lead to this. That will give you this. This is equation number 2. And in this case also the same thing is happened, that is this term is independent of x, that is this term is constant with respect to x, and this term is independent of t, that is this term is also constant with respect to t. So both of these are constant, that is taken as minus omega square. So the partial differential equation will give you two ordinary differential equation. One is 1 by t d to t by dt square, that is equal to c square by x, d to x by dx square, that is equal to omega square. So from here, two equations here, one is here and another is here, and this is the solution of this equation, and that will give you t is equal to a to the power e to the I omega t, that can also be written as a 1 cos omega t plus a 2 sin omega t, and this will give you the solution x function of x b e to the plus I omega c x, and that can be written as this. So the complete solution is this and this. So the solution for phi xt is written here. Now just separate, just multiply, just simplify this. So this can be from this relation you can write, just first multiply these with these two terms, that will give you these, and from here these and these. Just multiply this. Here is everything after multiplication. Now if we consider the situation of for simple harmonic motion, then the first and fourth terms, that is this is the first term cos omega t cos omega x by c, and this is the fourth term, that is sin omega x by c sin omega t. You know that the simple harmonic motion has the general solution that y is equal to a sin omega t, okay, cos omega t, a sin omega t minus theta. In this form you can write. So from this term and this term, you cannot write it as simple harmonic as the expression of simple harmonic motion. So then that from these two terms, that is second and the third term, the right here the second term, here is the second term, and the third term is here. So that is a2 b1 sin omega t cos omega x by c plus a1 b2 cos omega t sin omega x by c, that is equal to, just write a2 b1 and a1 b2, all are pretty constant, so you can take it as a. This multiplication I write for general condition, or for simplicity, or for in generality, it is written as a. Then sin omega t cos omega x by c plus cos omega t sin omega x by c, that is nothing but sin omega t plus omega x by c. Okay, so phi xt becomes a sin omega t plus omega by c. So it is simple harmonic. It is the simple equation of simple harmonic motion. So second problem is also solved here. Next problem is find the steady state temperature. Okay, we will solve this problem. After going to the next problem. So I am leaving this. We will come back here after solving this problem. See here. After solving this problem. Okay. A function after solving this problem. Okay. A function v x y z of Cartesian coordinate x y z of a point satisfies the equation that square v is equal to 0. Obtain the possible solution of this equation by the method of separation of variables. Write down a solution satisfying the condition v x y z is equal to 0 for z is equal to 0, actually that is equal to 0, and v not is equal to 0 at points for which z is equal to 0. Now the function satisfies the Laplace equation here, since it is given that square v is equal to 0. So in Cartesian coordinate it can be written as del 2v by del x square plus del 2v by del y square plus del 2v by del z square, that is equal to 0. And to solve this, you can use the separation of variable method, and in that case v x y z can be written in this way. And then equation 1, just write these the partial derivatives in this expression, that will take the, then this expression will take the form y z d2x by dx square plus xy d2y by dy square plus xy d2z by dz square. Now dividing both sides by xyz, that will give you this, and from here you can write 1 by x d2x by dx square plus 1 by y d2y by dy square is equal to 1 by z d2z by dz square. And since the right hand side is only the function of z, and these are independent of the z function, so this both of these are constants, and this can be here 1 by z d2z by dz square, that is equal to p square, is a constant. Write it as a constant p square. So from here d2z by dz square is equal to minus p square z, that is equal to 0, and from here you have the solution z is equal to a1 into pz plus b1 into minus pz, because in this case you have two values for m, one is plus p and another is minus p. So that is the solution. And also say that these for these two terms are also separately will be constants, that are for the first term, this is here 1 by x d2x by dx square, that is equal to minus m square, and for the second one, that is equal to taken as minus n square. And obviously the condition to satisfy this equation, p square should be minus m square minus n square. Okay, now from this, if you solve this, you can get x is equal to a2 cos mx plus b2 sin mx, and from here y is equal to a3 cos ny plus b3 sin ny. So the complete solution is dxyz is a1 into pz plus b1 into minus pz, then this value here and then this value here. Remember, we will use this solution, the process, this solution in the just previous, in this problem number 12. Okay, in problem number 12. So let us now complete the solution of problem number 3. First do it, and then we will come back to the problem number 12. So here is dxy is equal to finally get it as this equation number is 2. Now the boundary conditions are here. At z is equal to 0, you know dxy and z is equal to 0, so it is 0, that is equal to 0. It was the first boundary condition. Then just apply here z is equal to 0. So 0. So this term will be 0, that is written here, and all these things here making z is equal to 0. So from here this term a1 plus b1. From this you will get a1 plus b1, and all this term will be constant. So a1 plus b1 and all these things are here. That will be 0. So a1 plus b1 will be 0, but a1 is equal to minus b1. a1 is equal to minus b1, and so vxy 0 will be a1, then since a1 and a1 is equal to minus b1, so here will be a minus sign with a1 outside the bracket. So a1 e to the pz minus e to the minus pz, and all the other terms is here. That is so that is vxy not equal to 0. This is the solution. Now come back to the solution number 12. That is here. Here is that in this case, find the steady state temperature distribution of a finite thin plate bounded by the lines x equal to 0, x equal to a, y equal to 0, y equal to b. The edges x equal to 0, x equal to a, and y equal to 0 being maintained at 0 temperature, while the edge b is maintained at the temperature fx. So if you write these in the form of boundary conditions, then you can write theta 0 y, that is that x equal to 0, and for any value of y that is equal to 0, and theta ay that is for value of a, that will also give you 0. That is for first this condition will this, and this condition is here this, and y is equal to 0, that is a theta a, here is y is equal to 0, and here is x, any value of x, that is also give you 0, and y is equal to b, that is equal to here x and b, that will give you fx. So all these boundary conditions are summarized here. Now the Laplace's equation in this case, since it is a two-dimensional case, so that will give you del 2 theta del x square plus del 2 theta del y square is equal to 0. So solution of this, I am not here to solve this because I am taking the solution of this expression. So where we have to come, just go to, this is two-dimensional case. So go here. That is the solution of problem number 3. That was 13. That was given here. Say here b is 5. So it is two-dimensional, so z component will not be there. So the term that will be here the first term, this term, and only this term. This term will not be there. So the solution will consist of these two terms. These two terms. So that is here written here. That is written here. That is written here. That is here. That is here. Phi xy is equal to phi xy is equal to, and the two values of e to the power py and minus py are separated here. Just separated here. So first one is e to the power py a cos px plus b sin px, and then plus e to the power py c cos px plus d sin px. This is the solution. And just go the same process. Just do the same process that was given in equation number 13, and finally you get the solution as this a1 p to the power pz, and this, and just then multiplication, complete the multiplication and take the constants this one as the common as. If you do that, then you will have that is written here. We will have the same that is written here. So this is the solution. Now using the boundary condition number 1, that is there, what is there, that is theta equal to 0 when x equal to 0. Now write this in this expression. So first term will give you e to the py, then a cos px, that will give you 1. So a e to the py, then plus b sin px will give you 0 result, and all and this sin px will give you 0 result. So from this term you will have a e to the power py, and from here this term will exist in this case. So c e to the minus py will be there, and that will be 0. Just put here x is equal to 0, you will get this. So from here, as e to the py and e to the minus py, you see here, since e to the py and e to the minus py cannot be 0 for the same value of y, it is not possible. So in this sense, there will be a equal to 0 and c is equal to 0, because the condition is there, only the condition is there that e to the power py cannot be equal to e to the minus py for the same value. So let us consider that y is equal to 1, py is equal to 1. So py is equal to 1 means e to the power 1, that means 2.73, and if it is 1, that is 1 by e, that means 1 by 2.70, that is different from the previous one. So e to the py and e to the minus py cannot be 0 for the same value of py. So in this sense, you can write from here a equal to 0 and c is equal to 0. So this term involving a and this term involving c will cancel, will not be there in the solution. So the solution now has the form phi xy, that is equal to e to the power py, then b sin px plus e to the power minus py, then d sin px. So this is the solution that will be now. Now the boundary condition number 2, that is at x is equal to a, theta is equal to 0. So that is theta equal to 0 is written here, and from this relation just use x is equal to a. So d e to the power py sin pa plus d e to the minus py sin pa, that is equal to 0. Or from here b to the power py plus d to the minus py sin pa is equal to 0. So sin p is equal to 0 from here, or pa is equal to n pi, and from here p is equal to n pi by a. N is equal to 1 to 3, etc. number. So qxy from here is bn e to the power, just write the value of p. So n pi. So in this expression n pi. In this expression, write this is in this expression pi xy is equal to bn e to the power n pi x by a, then dn e to the minus n pi y by a. So just write this expression. So this expression, okay. Now so sin p. So this expression y. So this will be y, okay. This is mistakenly written as x. These are will be y. This is will also be y. So the second term will be n pi y, sin py. So here will be d n pi y. That there will be n pi y. There will be n pi y by a. Okay. Then so this is the complete solution. So from this relation, if you write the value of p, then you will have this. And if you take all these values, then B should be replaced by Bn. Okay, all these things. Now, according to this condition, boundary condition number 3, that is when condition number 3 was here that theta x 0, when y is equal to 0, then theta equal to 0. So that will give you here, that is here, equation number 3 will give you, equation number 3 will give you Bn plus Dn sin n pi x by a from this relation equal to 0, or Bn plus Dn is equal to 0, or Bn is equal to minus Dn. Now just write the value of Bn and Dn in this expression. In this expression, that is in equation number 3. That will give you theta n xy, that is Dn e to the power minus n pi y by a minus e to the power n pi y by a sin n pi x by a. So this term actually give you e to the power n pi y by a minus e to the power n pi y by a. That will give you sin hyperbolic n pi y by a, 2 sin hyperbolic n pi y by a. So after simplification, that is given, I have 2dn. 2dn is here sin hyperbolic n pi y by a sin n pi x by a. So if you take all possible values of this value, write 2dn is equal to cn. Then this expression will give you q theta xy is equal to n is equal to 1 to infinity cn sin n pi y by a hyperbolic n pi y by a sin n pi x by a, where sin is equal to 2dn. So taking all values possible values of n. Now using the boundary condition number 4, that is fx, that is here, that is here, what was that? That was phi theta x b equal to fx. That is for the value of y is equal to b, it is fx. So that is done here. Fx is equal to n is equal to 0 to infinity in this, from this expression. Cn sin hyperbolic n pi b by a sin n pi x by a. So from here you multiply this term by sin n pi x by a, and then integrate it from 0 to a. That will give you fx sin n pi x by a dx, that is equal to that is will be 0 to a, then cn sin hyperbolic n pi b by a, then sin n pi x by a square will be there, and here take 2 is taken here, so half will be here, and that will lead you. And if you integrate this term can be written as 1 minus 2 cos 1 minus cos 2 n pi by x, and for the cos term, if you integrate the cos term, that will give you sin term. Sin term will give you 0. So only the integration that will give you the result for dx, and the dx integration 0 to a dx will give you a result, the result a. So along with this, there is a here, and from here cn can be calculated as 2y. Cn is equal to 2y this a sin hyperbolic n pi b by a 0 to a fx sin n pi x by dx. So here cn also calculated. Now problem number 3 is already solved, and problem number 14. Here is that suppose that the differential equation given here, and solve these with the boundary conditions. These are the boundary conditions, and we solved this type of problem several times. So I am not going through the detailed calculations. Just here is the expression, and this is the process of solving this expression. Every step is here, and finally the solution is taken. Just go through this. These steps. Go through the steps. Then that will give you txy is equal to a3, this and this. Okay, this is the solution. Now using the boundary condition tx and y is at infinity, that will give you from this relation that 0 is equal to this a e to the power infinity from here, and cos lambda x plus b sin lambda x, that is equal to 0. And from here you can write a cos lambda x plus b sin lambda x is equal to 0, and you can understand from here that for same values of lambda, for same values of x, both cos lambda x and sin lambda x cannot be 0. And in that sense, a and b both will be 0. And using this condition, the solution of t will be here. So in that case, a and b, the term related to a and b will not be there. So this term will not be there. So the solution will be txy is equal to e to the minus lambda y, and this is equation number 3. And number equal, if now use the condition 0 t0y, that is equal to 0, then from this expression e to the minus y, into C. From here only you get C, that is equal to 0, C is equal to 0. So finally you get Txy is equal to D to the minus lambda y sine lambda x. This is equation number 4. And another condition, that is Tay is equal to 0. If you use this in this expression, then that will give you D to the minus lambda y sine lambda a is equal to 0, and from here lambda is equal to m pi by a. And use this in this expression number 4. Txy is equal to D to the minus lambda n pi y by a sine n pi x by a. This is the solution. And now another condition also was there, that Tx for y is equal to 0 is equal to sine pi x by a. That is equal to, just write here this value, that is equal to d sine, and in this expression if you use y is equal to 0, then this will give you 1, the result 1. So this is equal, this should be d into sine n pi x by a. Now multiplying this term by sine pi x by a, and then integrate from 0 to a, that will give you sine pi x by a sine then sine n pi x by a, multiplying this equation by sine n pi x by a. This and dx, that is equal to dy 2, I am writing 2 here, so 2 should multiply here 0 to a sine n pi x by a square dx, and the solution of this will give you only the integration of dx, that is a, and d by 2 is here. So sine pi x by a is equal to d by 2, and this will give you 2 by a sine pi x by a. And now just write the value of d in this expression, that is Tx is equal to 2 by a e to the minus n pi by a y sine n pi x by a, and then this sine pi x by a. So this is the complete solution. If you take all values of n, then that will be given by this. Now come to the final one. Final one is the problem is here. Find the statistics temperature distribution in a thin plate bounded by the lines x equal to 0, x equal to L, y equal to 0, and y equal to infinity, assuming that the heat cannot escape from either surface of the plate, the edges x equal to 0 and x equal to L being kept at a temperature 0, and also lower edge y equal to 0 is kept at temperature fx, and the edge y equal to infinity at temperature 0. Now here is these conditions are summarized here, that theta is equal to 0 for x equal to 0 and y, that is any value of y, that is theta x equal to 0, y is equal to 0. The second one is theta equal to 0 for x equal to L, but y has some value. So that is theta is equal to x equal to L, y is equal to 0. Then theta is equal to fx for x, y both are 0. That is x is there but y is 0. So theta x, y is equal to 0 is equal to fx. And the last one is theta is equal to 0 for x, and x for value of x, any value of x, and y is equal to infinity, that is theta x, y is equal to infinity is equal to 0. These are the boundary conditions. And now here the Laplace equation in this two-dimensional case, since it is two-dimensional case, is del to t theta by del x square plus del to theta by del y square. Theta is a temperature function. And solution of this equation, you know, here is the solution, here is the process of solution. Go through this, and we did this type of solution many more times, several times, so I am going through the details. These are here, details are here written. So finally you get the solution as this, theta is equal to this, and that can be written as this. Okay, and finally from here you can write theta xy is equal to this. Okay, this for a1, a2, all these constants are given. Now to find the constant a, b, c or d in this expression a, b, c and d, we have to apply the boundary conditions. Now for the boundary condition number 1, theta at x equal to 0 and any value of y equal to 0, that will give you from this expression, that 0 is equal to e to the py a plus c to the minus 2py. Just put here the value of x equal to 0 and compute, that will give you this, and that is equal to 0. And from here a is equal to c e to the minus 2py. This is written as an equation. And from boundary condition 2, that is theta for any value of x and y is equal to infinity, that will give you that is boundary condition 4, that will give you from this relation, just use this value, use the value of y as infinity, e to the infinity, and this plus 0, that is equal to 0. And from a cos px plus b sin px is equal to 0. And for the same value of px, a and sin px and cos px cannot both 0 at a time. So a and b is equal to 0 in this case. So as a and b is equal to 0, from using this relation, c is also 0. So till now we find that A, B and C all are 0. So using A, B, C all are 0 in this expression, you will get, finally you will get a simplifier form, that is theta, theta will be here. What is that? That will be a simplifier form. That is, in that case, only the term relating involving d will be there. D will be there. That means the solution will be d sine px equal to py. So that is there. And now if we use the boundary condition number 2, that is theta is equal to 0 when y is equal to 0. So in this expression, where all these terms is not, but only d sine px equivalence py is there. So if you use y is equal to 0, then d sine px will give you 0 result. That is here, d sine px will give you 0 result. Or from this you can write p is equal to, you can compute p is equal to n pi by l. So now, considering all values of n, the solution would be theta is equal to n is equal to 1 to infinity, and then dn sine n pi x by l to the minus n pi by l into y. This is the complete solution. And now from the boundary condition that is given in number 3, that is theta x, and for y is equal to 0, so that is equal to fx, that is here. So in this expression, write y is equal to 0. That will give you somewhere in equal to dn sine n pi x by l, that is the fx. So multiplying this by sine n pi x by l and integrate from 0 to l, that will give you this, and then this term will give you half 0 to l to dn sine square n pi x by l dx. You can write this, and from this you can write dn by 2 1 minus cos this and dx, and the integration of this will give you sine term, and that will give you 0. So from here only the division of dx will be there, so that will give you dn by 2 into l. So from here dn is equal to, compute dn is equal to l by 2 0 to l fx sine n pi x by l dx. So the complete solution now, using the value of d, will turn into theta xy is equal to l by 2, l is 0 to infinity, and l is equal to integration l to 0 to l fx sine n pi x by l dx e to the minus n pi y by l. So this is the complete solution and final solution. So this is the end of this the lecture, and also the end of this chapter. So students, you go all the computations and practice it, and then all things will be clear to you.